had to given the, so somehow there are T temperature, T4 temperature, T1, T2, T3, T4 in the node at the center of the table. And the temperature in each node is equal to the average of the 4 nearest nodes. And the exercise was asking us to write a solution. So write a system of 4 equations whose solution gives estimate for the temperatures T1, T2, T4. And as Amara said, so how to do it, you have to consider for each node T1, the fact that the temperature is given by the average of the 4 nearest nodes. So it's like, we go first to the left and we have 10 degrees, and then to the north 20 degrees, and then T2, and then south T4 divided by 4. And then you can rewrite it and you have this equation, and then you do the same. So that's our first equation is just this one. And then the second equation, we do the same for the node T2. So it's T1 plus 20 plus 40 plus T3 over 4. And T3 is the same, T2, 40 plus 30 plus T4, and so on. So, Curatellan, sorry, I might mispronounce your name, I'm sorry. Is it a bit clearer now how to find the equation?
No, please repeat. Can you repeat it?
Yeah, so for the first one, you get the first equation. We need to use this fact here, so that the temperature at the node is approximately equal to the average of the 4 nearest nodes, to the left, above, to the right, and below. So for instance, let's do the first one, that is the one written here. So we take T1, and the temperature in T1 is the average of the node to the left. So T1 is equal to 10 plus 20. Here, the temperature is unknown, but we call it T2. And to the one below is the temperature T4, and it's the average. So we have to sum all of the nearest node and divide by 4. And so then just rewriting the equation, we get 4T1 minus T2 minus T4 equals 30. So let's try to do T2. So for T2 is equal to T1, right? Plus 20 plus 40 plus T3 divided by 4. So then we could rewrite it as 4T2 minus T1 minus T3 equal to 60. Okay? Okay. Okay. Now it's better?
Yes.
Good. Okay, good. And you could do that for all the four of them. So I'll give you the equation. So the system of equation is the following. The first one is, so 4T1 minus T2 minus T4 equals 30. That's the first one. And then 4T2 minus T1 minus T3 equals 60. And minus T2 plus 4T3 minus T4 equals 70. And minus T1 minus T3 plus 4t4 equal 40. And then the next things that the exercise was asking is how to come up with the matrix. So if you had to tell me the matrix of coefficient associated to the linear system of equation, what will it be? Maybe you could just write in the chat, for instance, the first row.
It will be 4, -1, 0, -1.
Exactly.
Minus
Yeah.
30.
So we only want, so the matrix of coefficient associated to the system is, so the first row, as Amara said, is 4, -1, 0, -1, because we see, so the 4 is the coefficient of T1, -1 is a coefficient of T2, T3 doesn't appear, so we have a coefficient 0, and minus T4, it's -1. So could you write in the chat the second row? So the one given by the second equation. So -1, 4, -1, 0, perfect. Do we all agree?
Yes.
And so similarly, then you do all the other ones, 0, -1, 4, -1, and -1, 0, -1, 4. Great. Perfect. Okay, so we solved together the first exercise. Great. So we can proceed, and I think you will, again, we are not that many, so I will encourage you to write maybe things in the chat, and then later on we could try to use Padlet, or as I said, since we are a small group, you could just even unmute yourself and freely ask questions, trying to interact with me. We are trying to do exercises together, so the more interaction we have, the better. And feel free to ask any question, any clarification at any time. I'm always happy to repeat if things are not clear, and so on. And I think also it might help if you have at the end a piece of paper or something where you can write, and I will ask you to compute some basic computation, so it will help if you have something where you can write. Maybe before we start, any question, or there is something that I should clarify from the lecture of this morning?
No, from me, I don't know if.
Okay, I'll assume that if people needs to have some clarification, just again, ask me. Okay. So I will start slowly with just a few recap of the things that we saw in the morning lecture. So again, if more people are joining, we don't start right away. So one of the last things that we said, it was focusing on the general form of a matrix. So we said that a matrix has a certain size that is given by the number of rows and the number of columns. So always the indices, the first index refers to the row and the second index refers to the column. And so in general, we said the M3 that correspond to the, let's say, ith row and j column is what we call ij. And this is a general form of a matrix. It might come handy to start focusing on matrices that have special property, and they have a special form where you have some condition on this aij. And the simplest possible matrix that you could think of are these two. So the null matrix, or sometimes called also the zero matrix, where basically every entry is just equal to 0. So no matter the size, we could have a zero matrix of different size, where every coefficient is 0. Okay, I see more people connecting, so maybe indeed some people were joining at 1:30. So hello, Laila, welcome back to the second session. So we just started with a quick recap, and we said first we recall the general form of a matrix, and now we started focusing on matrices that have a special form. So we said that,
hello to you and good afternoon.
hello, good afternoon. Sorry, I think there was a small misunderstanding with the time. So some people joined at 1, so that's why we started already, but we only did a warm-up exercise, and now we are probably starting with the material. So you didn't miss anything. And as I said, it will come handy if you have maybe a piece of paper where I will maybe try to, we are not that many, so it will be easy to do exercises together, and I will try to ask you to solve some basic exercises, and I'm always happy to take any question or necessity for clarification. So, so we can proceed. After the zero matrix, one of the matrix, again, the second probably easiest possible matrix is what's called the identity matrix. And the identity matrix is a square matrix. So we say that a matrix is square when the number of columns is equal to the number of rows. So it's n times n, the size. And we can have, for any n, we can have an identity matrix, and sometimes there is a small indices to keep track of the number of columns and the number of rows. And so it has the identity matrix as 1 along the diagonal and 0 otherwise. So if the indices are the same, we put 1, if not, we put 0. And do people know why is it called the identity matrix? Again, you can write it in the chat or just unmute yourself and say it.
Because we have just one as a constant in the whole matrix.
Sorry, Amara, it's not really easy to understand you. But I think what you were suggesting is let's try to see what happens when we apply the identity matrix. The identity matrix to a vector. So it was at the end of the last lecture, we saw that matrices are represents operators on vectors. And let's see what happens to understand why is it called the identity matrix. So let's take a vector x in Rn. So let's say that it has n entries, x1, xn, where each entry is a real number. So this is an element of R to the n. And we want to apply the identity matrix to X. So the identity matrix has 1 along the diagonal and 0 otherwise. So great, exactly. So as Amara said, so it's called the identity matrix Because if we apply to a vector, what we get back is exactly the same vector. And how do we compute that? Did you remember how we computed the product between the matrix and the vector? So we have we take the first row and we take the inner product with the vector. So we multiply each component, so 1 times x1. And then all the rest are 0, right? So the first row times the vector, the inner product will get just x1. And then if we do the same for the second column, we have 0 times x1 plus x1 times x2, and all the rest are 0. So we get x2 and so on. So we get back x. So x is the identity, right? That's why it's called the identity. So the identity matrix leaves the vector unchanged. Okay. Let's proceed with other special matrices. So do people have understood how to apply how to multiply a matrix and a vector together? I assume so. Then other matrices that have a special form. There are matrices that are diagonal, so that they have only non-zero element along the diagonal. So Aij is equal to 0 all the time that the indices are not the same. And again, we can speak of a diagonal matrix only when we have square matrices. So again, the number of rows is equal to the number of columns. Then there are other types of matrices that are important, that are lower or upper triangular matrix, where you only know that there is a triangle that can be above the main diagonal or below the diagonal, where you get 0. And here it's I wrote in terms of the entries. So I have 0 is one indices is smaller than the other, and so on the other types. So these are matrices that come up, just to start having some terminologies. And there at the end, I put just another class of matrices that is very important, especially in engineering problems, that are called sparse. So that means that there are more 0 entries than non-zero entries. So you will realize when you start doing matrix computation that if there are a lot of zeros, then computation are easier. It's also connected to somehow the storing capacity, the memory of your computer. If you have a lot of zero, you need less memory to store all the different, all the information encoded into the matrix. So somehow we really like sparse matrices, and there are all branches of mathematics that are connected to finding algorithm that allows you to have sparse matrices and how to work with them. So somehow this is an important class, and we like them because it's easier to work with them. Yeah, exactly. So we can think of an identity matrix as a sparse matrix. Yeah. Or even diagonal matrices are a specific type. So you might have also sparse matrices that are not so nice, in the sense that you might have, it's not easy to characterize where are the portion of your matrix where you have 0. It might be more chaotic, but diagonal matrices are an example. And they are among the nicest one. I mean, we really like diagonal matrices. It's much easier to work with them because then it's immediate how to compute the multiplication with a vector, for instance. So going back to the multiplication between a vectors and a matrix, we just computed in the very simple case of the identity matrix. We want to start doing some examples, studying some of the property of the matrix vector multiplication. And I want to just give you one small remark. So here we said that again, we have our generic matrix. Let's say that it's a m times n, and we apply it to a vector that it lives in our n. So the multiplication, so here let's say that our matrix is again an m times n, the size, and x is a column vector in our n. So we would get in the end a vector that lives in R to the m. And the entries are given by the inner product of the rows of our matrix A and X and the vector X. And another way of rewriting this, so we can rewrite this as AX, the vector. We could write it as, so we see here that here the first coefficient is always x1. And then what you have here instead is the first column of A. Then we have always the coefficient x2 and the second column. So that's how we want to rewrite it. We want to write it as x1, A11, AM1 plus x2, A12, AM2, AMN. Okay, so we are just rewriting it where these are the column vector of A. We write it in this way, A1, A2, A3. These are the column vector of A. So we could write the vector AX, the vector obtained applying the matrix A to the vector X, as x1, A1 plus x2 by 2. Where again, the xi, let's give it a different color. The xi are scalar, these are just numbers. And these are the column vector. And this expression is what we call the linear combination of vectors. So we have a certain number of vectors and we multiply them with scalars and we add them together. So this is what we call a linear combination. So we could interpret the multiplication between a matrix and a vector as the linear combination of the column of the matrix, where the coefficient, or sometimes are called the weights of the, this is a type, where the coefficient or the weights are given by the entries of the vector X. So we have two interpretations. One is more in terms of the rows of A. So we say that the multiplication between A and X is given by the inner product of the rows and A. That's the entries. Each entry is given in this way. Or we could say that the multiplication between A and X is given by the linear combination of the column of A, where the weights or the coefficient are exactly the entries of the vector X. So we have these two different way of interpreting the matrix vector multiplication. Now I want to start doing some properties, studying some of the property of this matrix vector multiplication, and we could try to do some exercises. Before I go to the exercises, any question on this double interpretation, either in terms of the rows of A or in terms of the columns of A? Okay, welcome to all the people joining. Everything is clear, that's great. So welcome to the people that just joined, and we're about to start doing some exercises together. So we want to do some exercises connected to the properties of the matrix vector product. So let's start with this very easy one. I give you a 3 times 3 matrix, this matrix A, and I give you 2 vectors, B1 and B2 in R3. So these are 3 times 1 in terms of size. These are column vector. And we want first, I ask you to compute A applied to 2B1 minus 3B2. So first you have to compute 2B1 minus 3B2, and then you have to apply the matrix A to this vector here. And so I'll give you a couple of minutes to do that, and maybe you can write in the chat the solution. So the solution will be vectors with 3 entries, and maybe you can write so ABC or something like that inside on the chat to see. And then I'll write the solution for everybody. Okay, I have an answer, minus 15 minus 18 minus 4. Do we all get the same answer? Minus 15 minus 27 minus 4. Okay, we have 2 different ones. What about the others? Then we could do it together. Okay. Yeah. Okay, another one. Yeah, I also got minus 15 minus 27 minus 4. So that's good. Let's try to do it together. And so we're really all on the same page. So we have this 2 vector here. And first we have to minus 2 minus B1 minus 3, B2. That's it's 1, so it's 2, so 4 minus 3 is 1, and then minus 9 minus 2. And then we get A applied to this vector. So let's write A again. So 1 minus, no, sorry, 1, 2 minus 1, 0, 3, 0, minus 2, 0, 1. So how to arrive to the solution? Then we have to consider, right, the inner product between these rows and this vector. So 1 times 1 plus 2 times minus 9. So we get 1 minus 18 plus 2 is minus 15. And then we get 3 times minus 9, so minus 27, because the rest are 0. And in the end, we get minus 2 times 1, so minus 2, 0, and again a minus 2. So it's minus 4. Great. So that's the first things that we got. So try now to compute instead first to a, so first apply A to B1. So this I just wrote again, who is A and who is B1 and B2. So first apply A to B1 and then multiply by 2. And then first apply A to B2 and then multiply the vector that you get for minus 3 and see what you got and see what you get. Okay, someone got already an answer and it's the same one as before. Let's see about the other. And for the people who just joined the call, so welcome everyone. And we're trying to solve some exercises together. This last one is about the property of the matrix and vector multiplication. So what about the other? So Amara said that she got the same answer as before. Same too, great, same. So let's do it together. It's indeed the same answer as before, and we'll see that that's always the case. Let's do it together. So first apply A to B1. So 1, 2, minus 1, 0, 3, 0, minus 2, 0, 1. Apply to the vector B1. So what do we get here? Again, could you write in the chat, what do we get? What is the vector that we obtain? AB1. So if we apply, yes, great. But if so, what about this vector here? So now that if we do all the steps together, so first, if we apply the matrix A is 3, 0, minus 5, that's great. And what about AB2? So still the same matrix, 1, 2, minus 1, 0, 3, 0, minus 2, 0, 1. Apply to 1, 3, 0. What vector do we obtain? 7, 9, minus 2, great. And so now if we multiply, if we take twice AB1 minus 3AB2, then we get exactly minus 15, minus 27, minus 4. So we see that this was exactly the same answer that we got when we applied A to the vector 2B1 minus 3B2. And this is always true in general. This is the property that it's called linearity of the matrix vector product. And we could try to prove it together. So we want to prove that when you are trying to multiply a matrix for a linear combination of vectors. So again, a linear combination means that we take two vectors and first we can multiply them by two scalars. So alpha and beta here are scalars. Let's give, so just real number, let's say. So is the same if we first do the linear combination and then we multiply for the matrix A, or if we apply the matrix A to the vectors and then we take a linear combination. And in general, we said that this is exactly, it's a linear combination of the column of A, where the coefficient are given by the entries of the vector. So in this case, we could write it in this way, where AK are the column of A. We go from 1 to n because we have n column. And we see that here, we could just rewrite it as A multiplying the sum for k that goes from 1 to n. Vk alpha k plus beta goes out of the sum, wk alpha k, ak. But these are exactly, is a linear combination of the column of A where the coefficients are given by V. So by definition, this is the matrix A applied to the vector V, plus beta, the matrix A applied to the vector W. So we proved it in general. We had verified it in an exercise, but we actually proved in general that there is this linearity between the matrix, the multiplication for a matrix and a vector. Okay, some more easy properties. We said we can multiply a matrix and a vector together. What about operations between matrices? There are some very easy ones. So adding and subtracting matrices together, that's very easy. So we just subtract and add the entries. So assume you can do that. So here I put a caveat at the beginning, something we should be careful. It makes sense to add and subtract only matrices of the same size, where they have the same number of rows and the same number of columns. And let's say that we do that. So we take A and B, where the size is exactly the same. They have m rows and n columns. And then you just have a new matrix if you add all the entries together or if you subtract all the entries together. So that's a very easy operations that you can have between matrices when they have the same size. Something slightly more complicated is instead considering the multiplication between two matrices. And that's what we want to do, now. And to understand matrix multiplication, it might be useful to remember the interpretation that we had of matrices as an operator. So remember at the beginning, we said that when we are multiplying a matrix for a vector, we are operating on this vector and we obtain a new vector. So we could consider a matrix as a representative or as associated to a transformation going from a set of vector to another set of vector. So this is what the setup that we are recalling now. So let's say that we start from, let's look at the picture. We start from a vector x in Rp, so all the entries of the vector are real number, and we have p of them, and we multiply by b, so we operate on the vector x, and we obtain a new vector in Rn. So we are assuming here that b is as size n times p. So it has n rows and p columns. So it takes a vector in Rp and it gives back as an output a vector in Rn. And then we do that again. So in this time, we start from a vector in Rn and we multiply by A our matrix that has size n times n. So we get back a matrix, we get back a vector that is the matrix A applied to the vector Bx, and that's a matrix, a vector, in Rn. So basically, we see that the vector that we obtain, the vector obtained after we multiply the matrix A to the vector Bx, is the product produced by a composition of operation. First, we multiply B, and then we multiply A. And we said before, right, this multiplication is what we call the linear transformation. So this time we don't have one, but we have two of them at the same time. And what we would like to do, we have this operation of two linear transformation composed to each other, so multiplying first by a matrix and then by another. And we would like to express this composition as a multiplication by a single matrix. So this is the goal. Represent this composition as a multiplication by a matrix that will be denoted as AB, the product of A and B. So a new matrix. So that exactly when we multiply the matrix A to the vector Bx is the same as multiplying the vector x from AB. Is the goal clear? This multiplication of matrices, composition of two operations. Great.
Yeah, sorry, I didn't get well. Dx, is it a vector or a matrix?
Bx is a vector. Is a vector that lives here in Rn. Because we start from a vector x, we apply a matrix, and we obtain a new vector that this time lives in Rn. So this is a vector that lives in Rn. And we are trying, so is it clear what we are trying to do? We want to, somehow consider we have these two operations that are given by the multiplication of two matrices. We are trying to do one operation instead of two, finding one single matrix that will be the product of the two that allow us to go from Rp directly to Rm. Let's try to do it. Let's try to understand what is the product of the two matrices. Again, stop me anytime if you would like to have any clarification. Let's try to do it together. So what is the starting point? We have our two matrices, A, that is size m times n, and B is n times p, two different sizes. And X is our vector here, that is a vector in Rp. And we can denote the column of B by B1, BP. We give them some name. And the entries of X by X1, XP. So maybe just to emphasize, these are vectors, right? First, we have B1, BP are the column vector of B, and X1, XP instead are the entries. So in terms of the BIs and an XIs, can you tell me what is BX? So BX, we just said it is a vector, and is exactly the vector given by if I want to, sorry.
Yeah, I think BS should be equal to X1, B1 plus linear combination.
Exactly. It's a linear combination of X1, B1. It's a linear combination of the column of B, where the weights of the combination are given by the entries of X. That was our definition. Great. So remember what we are trying to do. We are trying to find an expression of the composition of the multiplication for B and the multiplication by A with a single matrix. So far we applied B. Now we want to apply A, right? The second. So first we did this, and now we want to apply the second one. So A applied to the vector Bx means A applied to X1, B1 plus XP, BP. And here we use the property that we just proved, the linearity of the matrix vector multiplication. And what do we get? Can you tell me? Amara, it's not easy to understand you.
It's X1 A B1
Yeah,
plus
exactly.
X2 A B2.
So x, we multiply, the coefficient is x1, and then a applied to b1 plus xp a applied to bp. So we are saying that the vector here, after we apply the composition.
Sorry, I am a bit confused.
Yeah. Maybe I can repeat.
No, I have a question first because I thought maybe for this case n should be equal to p.
Sorry, can you repeat, please?
Because we have a, the size is m times n. Now applying to dx. So since dx, I see the size is a vector of p. So I don't know how the multiplication works.
So here we are applying basically a bx is a vector that lives in bx is a vector that lives here in Rn.
Okay. Okay.
And so where are we? So we start from a vector here in Rp. We apply b and we get a vector in Rn. That is a vector that is given by the linear combination of x1, b1 plus xp, bp. And the column vector of b are all inside Rp, right? We have, the column vector. So we have exactly p column vector, but each one will have n entries, okay? So the column of B, the matrix, lives in Rn. So I don't know if that was the confusion that you get. So we're summing together vectors in Rn. We have p of them, and we get the vector bx in Rn.
Okay, does it mean that the dx, the number of line, is equal to n?
Yeah, so basically here, if I want to write it, so these are vector, right? And each of them will live in Rn. So Bp will be a vector of entries, let's say Bp1, Bpn, and it lives inside Rn.
Yeah, very clear now. Thank you.
So we're summing together, and that gives us a vector in Rn. And that's good because so here, this is a m times n vector. This is a n times 1, is a column vector that lives in Rn. And what we'll obtain is a vector in Rm. Okay, an m times 1 vector. Okay, do we all agree?
Yeah.
Good. So we're saying that the vector A applying to Bx is a linear combination of vectors AB1, ABP, where the weights of the combination of the linear combination are given by the entries of X. But so what does it mean? I mean, it means exactly that the matrix that we are looking for has as column AB1, ABP, right? We said that when we apply a matrix to a vector, we get a linear combination of the column of the matrix where the entries, where the weights are the entries of X. And so we are looking for a matrix, and that's exactly the matrix whose column are given by this vector AB1, ABP. So we want to define the matrix given by the product of A and B as the matrix that has as column AB1, ABP. Sorry, there is a question. Was it a question or?
I guess no, it wasn't a question. Something.
No worries, no worries. Okay, and just note that the matrix that we obtain, what is the size? So we started from A that has size m times n. We multiply it by B that is n times p, and these two numbers need to be the same. In order for the product of the two matrices to be defined, these two numbers needs to agree. And if we go back to the picture of the multiplication, the fact that the two numbers agree means that first we go from B with B from Rp to Rn, and then we need to start again from Rn. Otherwise, it wouldn't be defined. If we have two different spaces, so two different numbers, then it wouldn't be defined the composition. So in order to have a well-defined product between the two matrices, these two numbers need to agree. And the matrix that we get in the end is a matrix of size m times p. So it represents a linear transformation going from Rp to Rm. Questions about this, about how to multiply the two matrices together that represent a composition of linear transformations?
No, but I was just wondering in which case we have A times B equal to B times A.
Okay, then we'll do it in a second. Just that's exactly one of the properties I want to discuss. So it's very good.
All right.
Before going there, maybe just to check if really, I mean, I'm not sure if some people maybe is the first time that I see it. Could we just compute quickly the multiplication between these two matrices? So you have A that is a 2 times 3 matrix and B that is a 3 times 2 matrix. So first, before going to the computation, we can already check what's going to be the size of A times B, right? So this is a 2 times 3. This is a 3 times 2. So these two numbers are the same. So that's good. The composition is well defined. And so A times B has size 2 times 2. So 2 columns and 2 rows. And maybe you can try to compute it and write it in the chat just as first row and second row, something like that. So we already have an answer. So Amara says first row -2, 7, second row 1, -3. Let's see, someone else, -2, 7, 1, -3, great. Let's wait for a third one to see. same, great. AB, so 2, 0, 1. Zero, 1, minus 1. Minus 1, 1, 0, 2, 0, 3. So we get, so the first entry is this one times this column. So minus 2, 0, 0, minus 2. And then, so this one times this one. So 2 times 2 is 4 plus 3. So we get 7. And then it's minus 1, 3. So correct. Well done. So this is again our 2 times 2 matrix. Great. So I already had a question. So is the product of two matrices commutative? So when we have two, let's say, real number and we do p times q, then it's commutative and p times q is equal to 2q times p. Here we have a new multiplication, the multiplication between matrices. Is it commutative? I get AB equal BA with a exclamation point. I'm not sure what it means. Amara says no. What about the others? Is it commutative or not? No. No. Yeah. Well, yeah, it's not commutative. And we could do some examples right away. Okay, that was the explanation of the exclamation point. Great. Let's do some easy examples so we can start also familiarizing with some computation. So we take the R2 plane, X and Y, and let's say that A is the following matrix, 0, 0, 0, 1. So this is what we call a projection matrix, because when we, so it operates on a vector, so it takes as an input a vector in the plane x1, x2. And when you project, so when you do the multiplication between A and the vector x1, x2, what you get as an answer is the vector 0, x2. So it means that you are projecting your vector onto the y-axis. That's why it's called a projection matrix. So that's our A. And then as B, we take the matrix that rotates a vector by an angle theta as before. Let's say that is pi over 4 counterclockwise. So it came up also in the first lecture as an example of our rotation. And in this case, our theta is pi over 4. So the matrix representing the rotation is cosine theta minus sin theta cos theta. And in this case, it's pi over 4. So we can substitute. So it's just the rotation. And then these are the two operations that we want to apply. And we want to see that in the end, they are not commutative. So let's do it together. First, we take, the vector 1, 1, and first we rotate by 45 degrees. So we apply B. And then we project. So first we do this. So first we apply B and then we apply A. So if we take X and we apply B, so if we rotate it, so remember B was this one, And if you do the computation, x is 1, 1, then what you get is bx, that is the vector 0 over the square root of 2. What happens when we apply a? Can you write in the chat what is the vector that we obtain after we apply a? Yeah, so the bx, so a is the projection along the y-axis. So in this case, if we project, so bx, it remains the same, right? Because it's already on the y-axis. So it's already, it coincides with the projection. So a of bx is still vector 0 of 0 and square root of 2, because it already belongs to the y-axis, right? So that's what we get in one case. Let's now invert the operation. So let's first project and then rotate. Is we first project, so first we apply a, and then we rotate. We obtain the following. So with the red arrows, I have a of x. So first we apply a. And what do we get? Remember, x is 1, 1. Can you tell me the coordinate of ax, the vector that we obtain after we multiply by a?
0, 1.
0, 1, right? We are projecting along the y-axis. And then we rotate by 45 degrees, and even without doing any computation, we see already that the two operations do not commute, right? And in fact, then you can compute that b applied to ax is the vector minus square root over 2 square root over 2. So we conclude that the vectors are not the same. So in general, it's not commutative. Ah, okay, I wrote it in the other. I forgot. So in general, we conclude that the multiplication between matrices is not commutative. Maybe some important remarks also to kind of conclude this series of properties is that in general, I don't have also cancellation law. So for matrices, even if we know that AB is equal to AC, this does not imply in general that B is equal to C. And I invite you to come up with some examples, for instance. And the same if we have that the product of two matrices is 0, you cannot conclude in general that either A is 0 or B is 0. And we'll do some exercises about that. So before I move to the other exercises, some questions on the matrix multiplication that we just saw, the example. Oh, well, good. So now I think for the last parts, we are approaching the end of the session. And I just thought that we could, I'll try to use Padlet, I'll experiment. So I'll put here a link in the chat. And I'll share my screen. So you should see here Padlet, where I put some questions here. And if you click on the link, you should be able to just access this even from your phone or your tablet or laptop, whatever you are connecting from. You should just have access to this, and you can just anonymously start writing solutions for this question that I put here. So let's see, try to experiment with this. So you can pick your favorite questions, and it doesn't matter, we don't need to go in order, and just try to come up with the possible solutions for the exercise. Maybe I can already put here a question, the final column. If you have some questions, you can put it here as well. So does the link work? Isan, maybe you could try to post just under any question, just a test to see if it's working.
Okay. I tested it, it works.
But I don't see.
Okay, just a minute.
I wanted to see if they're your answers. Okay, great. I see. So I hope that people are succeeding in True. Yeah. So I see. Can you always try to justify your answers? Maybe write a small explanation. Good, I see people are starting to put. Maybe I'll leave you a few minutes, and then in around, let's say 5 minutes, we could discuss some of the solution. The people that wrote yes and true, could you, in the fourth question, could you maybe elaborate and just write a small explanation? It doesn't need to be a formal proof, but maybe a few lines. The answer is correct, it's true. But maybe I'll take a quick toilet break, and when I'm back, we could discuss more. So I'll leave you a few minutes to experiment with the questions. I'm really happy that people enjoyed the workshop, and thanks again for engaging with all the exercises. I can stay a few minutes if there are more questions.
Can we divide two matrices?
Maybe I can say I had one final slide. So given that there is the question, I could say something. That's a very natural question. We said that we can multiply matrices together. Is there a kind of inverse operation? And that's exactly the final slide that I had. So we can conclude with that. So maybe that's so do you see back my iPad? So the screen of my iPad?
Yes.
So if you have a square matrix, you can say that there is an inverse for the matrix if you have a matrix that multiply to A on both sides. Remember that the multiplication is not commutative, gives you the identity. So you could think of this as a kind of inverse for the operation of multiplication. It doesn't, you don't have an inverse all the time. So, but if you have an inverse, if you have a matrix that admits an inverse, that you say that the matrix is regular. If the matrix does not admit an inverse, then you say that it's singular. So a priori, there's not an inverse every time. And maybe, I don't know, to conclude, if people have examples of matrices that admits or do not admit an inverse, maybe with respect to some of the operation that we considered in the afternoon. So somehow an inverse is an operation that undoes the operation that the matrix did. So first you apply one, and then you apply the inverse, and you go back to the original vector.
Does it mean that any square matrix is a singular matrix?
No, there are square matrices can be either singular or not. So for instance, if you remember the operation, if we consider A, the matrix 0, 0, 0, 1, That's a matrix that gives the projection onto the y-axis, right? You take a vector, let's say v, and you project it onto the y-axis. But you see that there are a lot of vectors that are projected onto the same point, right? So how can you construct an inverse is not one-to-one, right? Because you have a lot of vectors that are projected onto the y-axis. So it would be impossible to then send AX univocally onto another vector. So that's an example of a singular matrix.
Okay.
But for instance, instead the rotation can be an inverse, can be a reversible operation, and it can admit an inverse. So you have other example of a square matrix that admits an inverse. And maybe the numerical property that you can use to check if a matrix is singular or not is called computing the determinant. So we didn't have time today to go into that, but that's it. So it was a very natural question. Thanks a lot.
Okay, thank you.
And I will share with Ezan the slides also today if people are interested. The main reference is still the one that I had in the morning. So Matrix Computation and the book by Gilbert Strang. Maybe people are coming up with an example. Yeah, that's a regular matrix. So that's an example of non-singular ones. Thanks. Great. Yes, exactly. So thanks a lot. Thanks for engaging with me. Yes, exactly. So nice example in the chat.
Okay, thank you. Thank you.
So we continue tomorrow. Tomorrow we'll focus on the Gaussian elimination algorithm. So take linear system and learning how to manipulate matrices in order to solve the system.
Okay, thank you very much, Professor. This was really wonderful.
Thanks a lot.
And thanks, everybody.
Thanks, everybody. Thank you very much.
Thanks a lot.